Okay, good afternoon. Wow, those lights are bright. Okay, well, actually, this is perfectly timed because the last few questions, or at least the last few thoughts of the last session, were about efficiency and how do we make the ML problem a more tangible and basically easier to solve problem through adding efficiency. So what I'm going to talk about is ARM's approach to that. I'm going to give you a one-on-one on the problem space. None of that's new to anybody who's been sitting in this room for the last hour or so, but at least it gets us a place to start from. I'm going to talk a little bit about what our partners are doing already to address some of the challenges and some of the opportunities that this sort of burgeoning AI space is bringing. And then I'm going to talk about future architecture, the work we're doing around software, and some new product concepts that we're bringing to basically make this, to close the gap between where we are today and where people need to be with addressing AI. So first up, AI on ARM is already everywhere. The last speaker in the last session talked about how you have this movement. You start at the edge, whether that's in a mobile device or an IoT embedded device, or even perhaps in a car, right? So from the edge device back into the data center, and you're trying to solve that AI problem as early as you can in terms of where you're addressing the data that's coming in. So the focus of today's talk is primarily on the cloud and what we're doing in the cloud with generative AI and AI in the cloud solutions. So again, no surprise to anybody, just how much data is being generated, how much compute is being demanded from the training algorithms. The data explosion is something we haven't seen before in the infrastructure space. Now that's driving energy consumption. It's creating a sustainability challenge. It's also driving us closer and closer to the edge of where Moore's law can have an impact. And just if we look just at GPT-3, we're looking at a terawatt hour to train a GPT-3 model, which is generating about 500 tons of CO2. So it's clearly not something we can ignore, right? So as we're, and all the bright minds in this room are thinking about how to solve generative AI and how to build better models and how to make things more, capable, we also need to be focusing our energy on, energy, no pun intended, on how do we do that in an efficient way. Oops. So going back to the start of this, right? So frontier models, these very, very large models, have been maturing, right? We're seeing this maturing in the model data. We're seeing the iterations of models improve. But those trained models are not something that are going to get deployed, in a small form factor device or, being something that you actually want to do all of your compute on, right? When you get to the point where you're using applications, when you're using handheld devices, you've got to reduce those data, right? You've got to reduce the model. You've got to retrain the model. So there's a demand for two things. One is a more efficient model, so a smaller model that can be deployed local to the consumer. And the second thing is a model that is specific to the consumer's need, right? So if you have a model that is very generic, a very large frontier model, you're going to want to shrink that model and target it at a specific application space. So that's where we see things like retraining, tuning of models being quite important, and the ability to shape the models to the form factor that people are going to use. We're also seeing the inference and the energy required to run inference moving out into the user space, right? So moving from the data center, from the cloud, into where the consumer is handling the data. So thinking about how we build the models, these generative AI models, how we tune the models, how we shrink the models, is all part of how we look at building the architecture of these systems. Now, the frontier models and these large data sets are probably by necessity going to be built in large hyperscale data centers. those are the places where there is the capacity. Those are the places where they have the GPU compute. It's probably going to be led by a small number of hyperscalers. And they will remain power and cost intensive to build those large frontier models. That's what we should expect. However, that's obviously, and industry data on this indicates that's not the majority of the AI workload. What we're expecting to see is that 80+% of the AI workload is going to be this tuning, shrinking, inference, right? So the loading in these systems is going to be heavily dominated by what comes after you've built your frontier model. Just in the last year, the data, I think, is there's over 300 startups in this space looking at how do we build both software applications and hardware to drive more efficient use of inference and more efficient use of model shrinking. And the focus is clearly best TCO performance at scale, right? So how do you make it perform, how do you make it low cost, and how do you build it at scale? So in the data center, what we're seeing is we're seeing two forms of inference and two forms of evolution of these hardware systems. So on the one hand, you've got what happens on a CPU, and I'm sure that we're going to talk a little bit more about that in this session. That's where you've got the maximal performance for inference with an optimal TCO point. So you've got a processor, a CPU, you've got extensions and instruction set extensions that allow you to do inference in that CPU hardware. The second form is you've got an accelerator attached. So now you're attaching something like an Nvidia Grace, which I'm sure we'll or an Nvidia Hopper, rather, which I'm sure we'll talk about. And what's important there is how quickly can you talk from your CPU to your accelerator card. And the last presenter talked about just the memory bandwidth constraints and challenges, coherency, the need for both high bandwidth memory on your accelerator, and then larger capacity memory on your CPU. So what are we seeing so far in the industry? I already mentioned Nvidia, but the Nvidia Grace and the Nvidia Grace Hopper chips are basically providing that combination of high bandwidth memory and compute, and that's based on the Neoverse V2 CPU processor. We've got a very large amount of inference being done in traditional compute on AWS's Graviton 3 based on the Neoverse V1 processor. And we've got Ampere, New Reality, Nvidia Bluefield, and Octeon building both accelerator offload, in the case of New Reality, the Bluefield, and Marvell, or hosts that are hosting those accelerators. So you've got this combination of a host and accelerator being built with the application of the ARM technology. So that's what's out there today, and what are we looking forward towards? So CPUs are sort of the closest thing to the model when people are running their AI. So what we want to make sure is that it's very easy and very quick to turn around the analysis on the model if it's scalable and fits inside the CPU. So what have we been doing? So we started out with the ARM v8 instruction set. We added int8.product. And that's available in the Graviton 2 platform that AWS serves. We added bfloat16. So part of the conversation that we're hearing today is how do you reduce your granularity? How do you go from 32-bit data sets to 16-bit data sets to 8-bit data sets? And ultimately, the question is how do you get to 4-bit data sets? Because as you shrink the size of those data sizes, you're getting to multiply how many transactions you can basically run on the system, right? You're improving your loading. You move on from bfloat16, you add matrix multiplication as part of SVE, the SVE instruction set, and with the Neoverse V2, we got to SVE2, which is what you're seeing in the NVIDIA Grace system. Lastly, we are now adding the SME, scalable matrix extensions, to push to the next level where you can actually do a huge amount of actual matrix multiplication, which is the fundamental unit of compute inside of an AI accelerator. And all of those things come within the ARM well-curated, clean software ecosystem. And software is a key part of this whole puzzle, right? So as we look at the frameworks from PyTorch, Paddle, Onyx, all supported on ARM, we're also looking to make sure that we're embedding the ARM compute libraries for the most efficient execution of the model into the 1DNN runtime and the XLA and the TensorFlow RT runtimes. And that allows those runtimes to execute most efficiently on whether it's Neon, whether it's SVE, whether it's SME instruction set. With the goal being that you get the most efficient model to framework, to runtime, to compute library, to hardware transition, because that's kind of what the end user's looking at. So one last thing I want to talk about today is our compute subsystems. So if you go back to the picture I showed where people are building, they're looking at compute, but they're also looking at compute with accelerator. When they build a compute with accelerator today, the accelerator generally comes in the form of a PCIe attached form factor. Right? Now, PCIe attached form factor is good, but it has its constraints. Right? And the constraint is PCIe or potentially CXL. How do you improve the memory bandwidth from that accelerator to the CPU? And the way that we're proposing you do that is you integrate the CPU, the compute, into the same package as the accelerator. And to do that, what we're enabling people to do is to build their own compute in the most straightforward, time-to-market advantageous way by taking our compute subsystem. Later on today, Eddie Ramirez on our team will be talking about ARM Total Design, our new ecosystem of partners who are going to be helping people with the compute subsystem. But we're already seeing in silicon people using this ability to say, hey, I don't want to be a chip designer. I just want to have a chip, right? I want to have a chip and I want to integrate it with my accelerator. So by allowing people to take the compute subsystem and integrate it tightly with their accelerator, allows them that in-package proximity, and that gets them the memory bandwidth and it gets them the efficiency of the communication between those two. So just to wrap up real quick, so we all know inference at scale is going to be huge. Like I said, it's going to be probably 80% of what we see in the AI workloads. We're going to be driven very hard as hardware and architecture providers to provide very efficient solutions to solve that problem. We're continuing to innovate both at the architecture level and at the product level to make sure that that's as easy for people to build as they can. With that.
Thank you. All right, so I'll try to stay on time. I have too many slides as always. So I figured I would talk briefly about sort of GPU evolution in the AI space. So there were a number of talks earlier about various neural network applications, so I'll skip through those details. And I want to point out there was a lot of a history in AI and machine learning prior to 2012, but I'll sort of start mostly at 2012 when AlexNet was published. So since 2012, if we look at different neural network model architectures, we have convolutional neural networks, so CNNs, which were dominant for image tasks and still are going pretty strong. They were also used for some sequence tasks. They're less popular for those nowadays. We also had recurrent neural networks. They were really popular for sequence tasks up to 2017-ish. At which point transformers came out and started dominating that space. And today transformers are used obviously for various sequence tasks like language, but also they're coming into the image and video space as well. There also has been a very wide range of DNN sizes over time. Right? So AlexNet, I think, was about 50, 60 megabytes in size, if we look at the parameters, maybe a bit larger. The large language models nowadays get to hundreds of billions of parameters, so they're getting into terabytes in size. And recommended neural networks are actually even larger. They can get up to 10 terabytes in size and sometimes larger. So this obviously places different requirements on systems. So if we look at a little bit of history and images, on the very left we have 1989, so that's actually Yann LeCun in front of an x86 PC with an FP32 DSP card that they used to run digit recognition inference. I don't have the specs for that DSP, unfortunately. In the middle, we have Alex Krzyzewski's machine where he trained AlexNet in his dorm room in 2012. That has 2 GPUs, and between the 2 GPUs, there were about 3.2 teraflops of math horsepower. And then on the right, we have the Selene cluster at Nvidia, which came online in about 2020. On that, we trained a 530 billion parameter language model, did FP8 research and a number of other sessions. That in aggregate has, what's the number here? 1.3 exaflops of math throughput. So there's been a lot of change in between. Now, precisions are different, and we'll get into those details when talking about those flops. Interconnects have also evolved a lot, as well as did the memory systems, right? So if we'll just look at the interconnect, Alex's machine in 2012 had 2 GPUs. They would talk to each other through PCIe. I think that was PCIe Gen 2, so you had 80 gigabytes per second per direction. If we look at Selene, it has 2-level hierarchy for communication, intra-node and across the nodes, because you do have over 4,000 GPUs in the entire cluster. So it's InfiniBand across the nodes. Within the node, you have NVLink. NVLink had 300 gigabytes per second bandwidth per GPU, which is actually more than the memory bandwidth that Alex's machine had back in 2012. So if we look at the key aspects of AI systems, we can look at math units. That's where various instructions get executed to carry out the operations. And again, math intensity varies from neural network to neural network and across operations with the same network. Precision requirements for different operations also vary. Then you have the memory hierarchy, because you do have to feed those math units. You have interconnect, so various accelerators can talk to each other, because nowadays most models get trained in a distributed fashion. Even inference of large language models is distributed. You need I/O to actually feed the data into these neural networks and snapshot the models as they get trained. And lastly, we cannot ignore the software, because all of these components will not function without software, and there's a lot of software complexity that comes up. Okay, and so I'll take a look at the evolution along sort of 2 dimensions. So one dimension is just raw power or raw horsepower, right? So as process shrinks or you come up with a better design, you can increase throughput for math, memory, and so on. And then the smarts are basically using some application knowledge to go beyond what just the process shrink can get you. So if we take a look at, let's say, math format evolution over time, so starting from Fermi sort of in the top row, which was the GPU 13 years ago, ending at Hopper, which is the latest GPU from Nvidia. If we look at the FP32 column, where AI started out, there's been an about 40, 45x improvement, right? So that's just the raw horsepower, and that's what raw power buys you. And then going left to right, you sort of see what the smarts can deliver to you. So if we look sort of diagonally from where we started in 2010, actually, we can sort of take a look at it this way. So AlexNet was trained on the Fermi GPU that had 1.6 teraflops of FP32, or so single precision floating point math. And then Megatron neural network was trained on Ampere cluster on Selene. And that per GPU had 311 or 312 teraflops per GPU, but that was FP16. Right, so that was an improvement both from process and addition of tensor cores, as well as reduced data type. And then if we look at Hopper, so Hopper introduced OCP FP8, which goes up to almost 2 petaflops of math throughput per GPU. And there are further smarts that are being added in. Right? So with Ampere generation, we introduced 50% sparsity. Right? With that capability, you effectively double the throughputs listed on the table. And just today, OCP published microexponent format that goes to formats that are smaller than 8 bits per element. So it goes down to 6-bit types as well as 4-bit types. So we still continue to progress in both directions. Memory evolution had to keep up as well. So really quickly, I'm not going to delve into all the details, but if we look at the GPU DRAM from Alex's machine in the dorm room, there's been about a 60x increase in the amount of memory per GPU, right? So now we're up to 96 gigabytes per GPU. If we look at the entire system for training a neural network, there the increase in total RAM has been about 15,000x, right? Because we're going from a single machine with 2 GPUs to a large cluster with thousands of GPUs. Bandwidth has increased as well, but as you can see, that's sort of the smallest increase over time. So per GPU bandwidth increased by almost 20x. But again, system-wide, because we scaled out pretty widely, it's gone over by over 23,000 times. So that's just the raw power aspect. And the smarts have been sort of adjusting cache sizes on a GPU, adding special memory access units, so TMA, so tensor memory access, and Hopper GPUs to help with efficient access to memory to feed the tensor cores. Also, address translation units have to be adapted to deal with much larger memory spaces and different access patterns. Going beyond that, there's interconnect evolution as well, and that's driven by several aspects. So training scale has increased over the past, roughly 10 years by thousands of times, right? We went really from a single accelerator being used to train a neural network all the way to many thousands nowadays. Communication patterns have also evolved because of that, right? So before it used to be just point-to-point, if two GPUs were talking to each other. Nowadays you have, all reduce, all gather, reduce, scatter, all-to-all, point-to-point communications as well. So there are a lot of patterns to be satisfied, and some of those do require compute. So bandwidth per GPU has gone up. Basically kind of doubles with each generation of interconnect technology. But on the smarts end, which is almost more interesting, is that we do now start seeing networks performing some math operations. So let's say that's Sharp in the switches, various Bluefield and other smart NICs also do some math. I think I have a brief slide on that here. Yeah. So if we look at DPUs, so Bluefield 3, I'll skip through all the details, but what that enables effectively by putting ARM cores on the NIC and a few other accelerators as well, and giving it up to 32 gigabytes of memory, you can offload a bunch of communication-related computation from GPU or CPU. Right, so if your network switches do not have math, then you can actually use DPUs to do the math and offload the accelerator from that. For those operations, you can also do format conversions, layout changes as you're communicating data and so forth. And again, all of that conserves bandwidth on the accelerator itself, because that would require multiple accesses to memory, leaving more of that bandwidth to feed math units to continue training. Then, as was mentioned earlier, there's also a Grace Hopper superchip architecture where we combine two chips. So there is a CPU made up of ARM cores as well as a Hopper GPU. And they are connected through a high bandwidth bus, so C2C chip-to-chip bus, that in duplex mode has 900 gigabytes per second bandwidth. So now GPU can talk to CPU memory and access it directly in a cache coherent way at up to 900 gigabytes per second. It also has PCIe connections for NICs and so forth. Now, what that enables from AI's point of view are things like offloading some computation to CPU, or even offloading portions of the model to the larger CPU memory, because the CPU in this case can have up to 512 gigabytes of memory. And GPU has pretty high bandwidth access to it. You get tight interaction between CPU and GPU. These systems also enable larger scale out with NVLink. So with Grace Hopper, you can scale out up to 256 of these Grace Hopper modules, and they would be connected to each other via NVLink switches. And lastly, so software and programmability. So as we've seen, AI models keep evolving. Even if we just look at CNNs, there are plain convolutions, and then people keep inventing new variants. Right? There were depth-wise separable convolutions, group convolutions, deformable convolutions, and so on and so forth. So those have to be programmed, so it's important to expose programmability to whichever processor you are shipping, so people can innovate. Transformers also keep changing their architectures, right? There are different mixtures of experts approaches, different attention variants, multi-head attention, multi-query attention, and so on and so forth. So also as systems evolve and their smarts evolve, software has to also adjust to take advantage of those extra smarts. So as a result of that, programming has also evolved. Back in 2012, somebody programmed in CUDA for the GPU and used some framework to train a neural network. Oftentimes they were custom frameworks that people wrote for that task. So for example, Alex wrote a framework just for that task himself. If we fast forward to today, there are many layers of software. So you still have CUDA that gives you ultimate programmability for the GPU, so you can implement new operations and extract all the efficiency that you want. But we do have math libraries that implement convolutions and other basic operations out of which neural networks get built. There are communication libraries like Nickel, UCX, and ReachMem for interaction across different GPUs and CPUs. You have your frameworks into which all of these plug in, so PyTorch, JAX, inference engines as well. And then now you're starting to see toolkits that are getting built on top of frameworks for people to quickly build new large models. So for example, NeMo right? It's built on top of PyTorch, but it's sort of designed to facilitate language model investigations. So I think with that, I'm a little over time, so I'll stop here. Thank you.
Hello, my name is Song. I'm the Senior Director and the Data Centers GPU Chief Engineer at AMD. So I would like to talk about the hardware architecture and also the AI evolution of the Instinct family GPU. So back on the 2015-17 timeframe, and AMD launched the MI8 GPU with HBM 1.0, and also released the initial ROCm and to support the device driver, and that is it's going to target for the high performance compute application. And moving forward to 2016 to 18, we launched another series of the products called MI25. It is built with the HBM 2.0, and also that we also released the library of the ROCm to support the machine learning as well. So in 2016 and 18, and we actually rolled out another compute GPU that has the 60 compute units, and also with addition of the deep learning operation as well. And it's packed with the 4 stack of HBM2. And also, we also released the initial ML framework, right? And support the TensorFlow and also the Caffe as well. And the product that we introduced is that beside the PCI form factor, right? And we also enable the interconnect between the 2 or among 4 GPU through the Infinity Fabric as well. In 2008, we have seen that the amount of compute is getting larger and larger with the evolution of the new workload. And we started to have a deep collaboration with OCP to come up with a new form factor to support the AI and the machine learning needs. And we worked across with a few OCP member, and then we define and come up with what we call the OAM specification and contribute that spec into the OCP OAI sub-project in the server project. And the target application for this is going to be come along with the AOAM plus the UBB. Is targeting for the high performance compute and also for the AI acceleration. Back in 2019 and 20, and we rolled out the MI100. It's come with the 120 compute unit and with the matrix core engine added, and the performance at the FP16 throughput is gaining like 6.8x over the previous generation. And at the same time that we enable the PyTorch as well in the ROCm. And with this GPU, we also come up with the compute optimized GPU architecture called CDNA. The CDNA is targeting for the high performance compute application. Along with that, we introduced 2 products with the MI100. One is the PCI form factor. It's target for the general AI market and HPC as well. And at the same time that we roll out the OAM form factor for the strategic development and the exploration. So MI250 is one of the GPU that come with the 220 compute units. It gained 2x of the performance over the previous generation on the FP16 throughput, and it packed with the 8 stack of the HBM2E. And we also enable the exascale HPC application in the ROCm as well. And There are three, it was ranked number 1 and number 3, number 11 of the top 500 supercomputer list. And we have a deep engagement and collaboration with the other company as well, such as AI2 on the open language model, and also work closely and collaboration with the Hugging Face on the NLP model as well. And AMD also joined the new PyTorch Foundation as a founding member, in order to accelerate all the AI and ML capability. Instinct MI300 is the latest GPU that is going to be introduced here. It's come with the CDNA 3 architecture. And the silicon itself comes with the 192 gigabyte HBM3 memory. And the memory bandwidth can up to 5.2 terabyte per second. Along with that, we also packed with the high-speed SerDes. The Infinity Fabric bandwidth can up to 896 gigabyte per second. And the total the transistor of the GPU is around 153 billion transistor. And the product that we're going to introduce and roll out is OAM and the UBB base, and it's comply with the OCP OAI 2.0 form factor. It comes with the AMI300X along with the UBB 2.0. The total memory, high bandwidth memory is around the 1.5 terabyte. So AMD have been involved in the OCP server project and also the OS sub project, and we will continue to contribute and on the next generation product. Along with that, we're also going to have a deep collaboration with other work groups as well, such as the rack and power, the data center cooling work group as well, for the next generation of the AI HPC product. Thank you.
Good afternoon, everybody. This is Kannan Heeranam. I'm part of data center and AI organization within Intel. I know everybody is quite serious right now, very involved. You know, all the numbers are in your head. I'm not going to give you a lot of numbers today. I'm not going to talk about a lot of our products also today. But I do want to actually very briefly show this only to skip so I can save a minute. So you all saw some version of this slide already, right? The message here is that the energy consumption for running these generative AI models is just humongous. And this graph doesn't even have the trillion parameter model that we already started hearing about. So I will skip that and use the minute or two that I save here to give a story a little bit to lighten the mood here. So I am a big hoarder, right? I'm actually big on trying to reuse as much as possible. And for those of you who grew up in India, this is probably a familiar story. This is all made-up story on the moment, so excuse me if it doesn't go well. We don't throw anything away, right, growing up in India. So if you go buy a jar of coffee powder or those energy drink like Boost and Horlicks, I don't know if you are here, we don't throw them. We reuse them. We reuse them, we fill in some spices, we fill in some kitchen powders, whatever, and then we keep them and we don't reuse. I mean, we do reuse, we don't throw them. Now, one time what happened was, we got newly married and we used to live in the UK, so my wife wanted to make me a cup of Horlicks. She actually took what she thought is Horlicks from a Horlicks bottle and then gave me a spicy drink. So reuse is absolutely necessary, but it is easier said than done if you're not careful when you're reusing. Right? So with that said, actually, I'll just talk about level setting on a primer on defining emissions here, right? Which is very important, and for Intel, it is a huge thing. So there are three scope of emissions that we talk about, right? The scope one is really the emissions that directly come out of, say in Intel's case, our facilities and our factories and the transportation. that we do. And then the second one is the direct power consumption that we actually have in order to run our facilities, right? That's huge. And then the third one is 15 different energy emissions category that we track as part of running our business, right? So when we talk about embodied product carbon footprint, we really talk about scope 1, scope 2, and then the upstream scope 3, right? So Intel is on a journey to deliver life-changing technologies for every person on the planet, and we want to do it in the most sustainable way, right? Sustainable computing for a sustainable future is our mission, and we do focus on that in 3 different vectors, right? One is our reduction of environmental footprint in our manufacturing process and the supply chain that feeds into it. And then the other one is we think about designing sustainability into all our products that we actually design, right? And then we do collaborate with industry partners, like in the case of OCP, to actually drive our mission forward, right? So this is where our hefty, audacious goals are when it comes to sustainability. We focus on climate and energy, water and wastage. So we want to be net zero greenhouse gas emissions by 2040, right? So we are around the end of 2022 at 93% for renewable electricity usage, right? And we want to conserve water, right? So our hefty goal is by 2030, we want to actually be net positive by conserving 60 billion gallons of water, right? So again, 9.6 billion gallons conserved so far as of 2022. And we are already net positive in US and India with our facilities. And when it comes to wastage by 2030, we want to achieve zero total waste to landfill. And we are currently at around 6.4% as such, right? So sustainability is a big thing. And especially with Intel's audacious move into opening up our factories for anybody to come and design, we take sustainability very, very seriously, right? And the Sapphire Rapids, which is the 4th generation Intel Xeon scalable processor, is a flagship product from us, where we integrated advanced matrix extensions, TML operations within the Xeon processor, which is integrated boost for running your AI workloads. And we actually did all this with the renewable electricity, the water conservation, reclamation, and the circular economic strategies for waste, right? So we are at like 6.4 total wastage. At this point in time, we are working to reduce that drastically, right? So in terms of our roadmap, right, so all our products are actually going to go through the same sustainability principles and the goals that we have taken. Specifically, when it comes to AI, we have Habana Gaudi 2, which is a state-of-the-art ASIC chip for accelerating generative AI workloads. So I deal with a lot of customers every day, and the scale is only increasing and getting complex day by day. We started with the generative AI journey with one of our customers who actually opened up around 50 years worth of data, around 8 to 10 terabytes of data, for us to train the model for them. And the next customer simply doubled that amount, right? So the amount of energy that generative AI is demanding is very real, and the possibilities are also actually, very promising. This is not just a hype cycle that we live in, especially with generative AI. So we have audacious goals with developing our products in the most sustainable manner. We are going to continue innovating on the Gaudi line of products. And we are also actually going to continue innovating on the GPU side, and we will have the next generation GPU, which will fuse both the ASIC IP and the GPU IPs, and all of this in the most sustainable manner. And our commitment to sustainability, I don't know why this slide is incomplete. I'm sorry. But I just want to actually drive home the point that sustainability is not something that any one corporation can actually achieve on their own. So we partner with Mila and Professor Yoshua Bengio to really move the needle in terms of creating a sustainable future. Right? So we work with Mila on 3 different topics. One is climate change, one is materials discovery, and then the other one is drug discovery. Right? So all these 3 areas are very important for both Mila and Yoshua and Intel. And so far, the partnership actually started in September 2022. So far, we have either submitted or presented around 20 different papers, right? So if you want to actually go look up Honeybee, which is our very recent large language model for material science and materials discovery, which is a huge step in the direction that we are taking. So while we are moving the needle on embracing generative AI and developing state-of-the-art products and releasing them, sustainability is a huge part of what we do. And with the partnerships like how we do research fundamentally to change the world with the likes of Mila is very, very important for us. And with that, I wish you all a good conference. Thank you very much.